December 1940, Montreal. A McGill University professor stood in the darkness, watching an aircraft descend through the night. Edmund Godfrey Burr had been tasked with evaluating night observation instruments for Canada's National Research Council. What he witnessed that night would change naval warfare in the Atlantic. The aircraft, silhouetted black against the never-quite-dark winter sky, suddenly vanished. Not through fog or clouds. The plane simply ceased to exist. Light reflecting from fresh snow had illuminated its underside just enough to match the sky's luminance. Perfect invisibility. Diffused lighting camouflage had just revealed itself, and within weeks, British and Canadian engineers would attempt something no navy had ever achieved: making warships disappear. The problem facing the Royal Navy in late 1940 was brutally simple. German U-boats were winning the Battle of the Atlantic. Night after night, wolf packs surfaced to attack convoys, their commanders using the darkness as cover. The submarines sat low in the water, nearly invisible against the Black Sea, but convoy ships towered above the horizon, dark shapes silhouetted perfectly against the slightly brighter night sky. A U-boat commander could spot a merchant vessel at distances exceeding 9,000 yards under clear conditions. The escorts protecting these convoys could barely see 2,000 yards. The mathematics of survival demanded a solution. Standard camouflage paint offered no answer. Gray schemes worked in daylight, but at night, every ship became a black cutout against the sky. Dazzle patterns confused range estimation, but did nothing about visibility itself. The Royal Canadian Navy needed revolutionary thinking. When Burr's report reached Naval Services headquarters in January 1941, engineers immediately understood its implications. If reflected light could hide an aircraft, projected light might conceal a ship. But how would such a system actually function? The concept seemed to defy physics. Project light onto a ship's Hark hull to make it brighter. Match that brightness exactly to the night sky behind it. The ship's silhouette would dissolve. No contrast meant no detection. Counter-illumination, as Burr termed his discovery, promised to reverse the tactical advantage submarines had exploited since 1939. Laboratory tests proved the principle worked. Small models illuminated against dark backgrounds disappeared when the light intensity matched the surrounding brightness. Scaling this to operational warships presented extraordinary challenges. How many projectors would be required? What color temperature? How would operators adjust brightness as sky conditions changed? The Canadian Navy selected the newly commissioned corvette HMCS Cobalt for the first sea trials in January 1941. Cobalt's initial installation was crude. Ordinary projectors, the kind found in cinemas, mounted on temporary wooden platforms fixed to the hull's port side. The projectors aimed inward, washing the gray steel with light. Brightness control was entirely manual, requiring constant adjustment by an operator watching the sky and the hull simultaneously. The projectors were neither waterproof nor shock-resistant. Salt spray and rough seas destroyed several units within days. Yet the trials produced remarkable results. Observer ships reported that Cobalt's port side appeared 40% less visible than her unlighted starboard side. The Royal Navy took immediate notice. By March 1941, the corvette HMS Trillium had been fitted with Canadian equipment for parallel trials in the Clyde approaches. The Admiralty's report noted that under specific weather conditions, the crude equipment gave highly satisfactory results. Winston Churchill himself reviewed the findings, commenting that the business should be pressed forward on a broader front than one ship. Development accelerated. The second Canadian prototype addressed the color problem. Electric lamps at low intensity produce reddish light, similar to a dimmed household bulb. The night sky is never red. It contains blues and greens, the residual scatter of moonlight and starlight. HMCS Chambly received modified projectors in May 1941. Blue-green filters covered each lens, removing the unwanted red wavelengths. The platforms became retractable, allowing the delicate equipment to be stowed during daylight operations or heavy weather. Chambly's trials produced visibility reductions of 50% in most conditions and up to 75% on particularly dark nights. A U-boat that could normally spot a corvette at 8,000 yards might not see Chambly until 2,000 yards. That 4-mile difference represented the margin between life and death. The third version incorporated automation. A photocell measured sky brightness. A second sensor measured the light reflecting from the ship's hull. Electronic circuits compared the two readings and adjusted the projectors automatically. No human judgment required, no human reaction time limiting responsiveness. HMCS Kamloops carried this system to sea in September 1941. The trials were promising, but revealed new problems. The electronic control system was slow to respond when cloud cover changed rapidly. The photocells proved unreliable in salt air. Maintenance demands were extraordinary. British engineers at the General Electric Company developed their own version. More robust projectors, different mounting systems, manual control deemed more reliable than Canadian automation. HMS Largs, an ocean boarding vessel, received a complete installation in late 1941. The ship carried projectors mounted on brackets all around her hull. 2 rows ran the length of each side. Additional projectors illuminated the superstructure, funnel, and masts. 60 projectors in total. The installation represented hundreds of hours of engineering work. Largs conducted systematic trials between January and February 1942. Surface observation ships recorded visibility ranges under various conditions. Hudson bombers flew overhead on clear nights, noting detection distances. The results varied wildly. On the exceptionally clear, moonless night of 29th to 30th January 1942, Largs, unlighted, could be seen with the naked eye at 5,250 yards. With her diffused lighting operating, visibility dropped to 2,250 yards, a 57% reduction, the best result achieved by any vessel in the program. Average reductions across all conditions measured around 25% through binoculars, 33% with the naked eye. If you're finding this deep dive into British naval innovation interesting, subscribing helps keep these technical histories coming. The Royal Navy installed similar equipment on HMS Penelope, a light cruiser operating in the Mediterranean. 60 projectors covered her considerably larger hull. The wiring diagrams alone filled multiple pages. Each projector required individual power feeds, control lines, and manual brightness adjustments. The complexity was staggering. Operating the system demanded a dedicated crew of electricians. Across the Atlantic, the United States Navy had begun its own experiments. The supply ship HMS Hamel received an automatic diffused lighting system built by General Electric of New York. American engineers developed sealed beam projectors rated at 500 watts, far more powerful than British or Canadian equivalents. The control system used vacuum tube circuits, more sophisticated than anything attempted in Britain. Hamel's trials in early 1942 showed promise, but the U.S. Navy halted further work by mid-year. American doctrine increasingly favored radar over optical deception. The equipment and documentation were shipped to Canada's National Research Council. Canadian engineers installed the American system on 2 corvettes in 1943. HMCS Edmundston, and HMCS Rimouski. Each vessel carried approximately 60 projectors. Those mounted on the hull used retractable supports identical to earlier Canadian designs. Superstructure projectors were fixed. The electrical load approached 30 kilowatts when fully illuminated, roughly equivalent to 300 household lamps. Generators struggled under the demand. Systematic testing in St. Margaret's Bay, Nova Scotia, produced laboratory reductions approaching 70% under optimal conditions. Operational deployment told a different story. Rimouski escorted Atlantic convoys through the autumn of 1943, her diffused lighting system active during night watches. The equipment malfunctioned constantly. Vibration loosened connections. Salt corrosion attacked the electrical contacts. The automatic control system responded too slowly when sky brightness changed. Canadian engineers considered the light output too green, creating an unnatural glow that experienced observers could identify. Worse, the system consumed so much electrical power that other ship systems occasionally browned out. Yet, Rimouski achieved one operational success. On a September night in 1943, intelligence reports located German submarine U-536 in the Baie des Chaleurs. Rimouski, using her diffused lighting combined with carefully positioned navigation lights, approached the U-boat's reported position. The plan was to appear as a small fishing vessel, inoffensive and unworthy of attack. The deception apparently worked. U-536's commander, Kapitänleutnant Rolf Schauenberg, did not detect the corvette's approach. The subsequent attack failed when a mistimed shore signal alerted the submarine, allowing U-536 to dive and escape. But the tactical principle had been proven. Diffused lighting could deceive an expert U-boat commander at close range. By June 1942, Royal Navy commanders had reached a different conclusion. The enemy now used radio direction finding and increasingly sophisticated hydrophones. Visual detection was becoming secondary. RDF could locate a convoy regardless of camouflage. Submarine hydrophones heard propeller noise at ranges exceeding any visual contact. The Admiralty's assessment was blunt. Diffused lighting was impractical given other detection methods. Development ceased in April 1943, though discussions with the Canadian Navy continued through the war's end. The Battle of the Atlantic had already turned. Centimeter radar gave escorts unprecedented detection capability. Code breaking through ultra-intelligence revealed U-boat positions before they found convoys. Long-range aircraft closed the mid-Atlantic air gap where submarines had operated with impunity. Better escort tactics, support groups, and increasing numbers of convoy defenders overwhelmed the U-boat fleet. Diffused lighting, for all its technical elegance, had become obsolete before reaching operational maturity. The technology found unexpected application in aircraft. American researchers adapted the counter-illumination principle into Yehudi lights, named through obscure reference to a popular radio comedian. Instead of illuminating the aircraft's skin, Yehudi lights projected forward from the nose and wing leading edges. The light traveled toward potential observers, matching sky brightness from the submarine's perspective. B-24 Liberators and Avenger torpedo bombers received installations from 1943 onwards. Trials showed the system could delay visual detection by critical seconds, potentially allowing depth charge attacks before U-boats could dive. But radar again made the technology redundant. By 1945, aircraft detected submarines electronically, making optical camouflage irrelevant. The diffused lighting program produced no permanent installations on combat vessels. None of the prototype ships retained their systems after trials concluded. The projectors, control panels, and wiring were stripped out. HMCS Rimouski and Edmundston returned to standard configuration. The technology that had promised invisibility left no physical legacy. Yet the principle endured in unexpected ways. Modern stealth aircraft employ active infrared suppression, using cooled exhausts and heat-absorbing coatings to match background temperatures. Night vision systems now dominate naval warfare, operating in infrared wavelengths where diffused lighting concepts remain theoretically viable. Marine biologists studying counter-illumination in squid and other deep-sea organisms cite Burr's wartime research as foundational work in understanding adaptive camouflage. The complete technical archive resides in Canada's National Research Council records and Britain's National Archives at Kew. Researchers can examine the original circuit diagrams, trial reports, and operational assessments. HMS logs photographs showing her illuminated hull remain among the clearest documentation of the technology in operation. The images capture something extraordinary: a warship glowing with artificial light, attempting to vanish into darkness through the calculated application of physics. If you're finding this deep dive engaging, subscribing helps keep these intellectual explorations alive. The images capture something extraordinary: a warship glowing with artificial light, attempting to vanish into darkness through the calculated application of physics. Edmund Godfrey Burr returned to academic work after 1945, teaching electrical engineering at McGill until his retirement. His publications on diffused lighting camouflage, presented to the Royal Society of Canada in 1947 and 1948, remain the definitive technical descriptions of the system. No subsequent researcher has improved upon his fundamental insight that invisibility in darkness requires not shadow, but precisely matched illumination. The U-boats that might have been deceived now rest on the Atlantic floor. The corvettes that tested Burr's discovery were scrapped decades ago. But the principle endures, proven possible even if ultimately impractical. A remarkable attempt to paint ships with light and make them vanish into the night sky they sailed beneath.